Hello everyone, and welcome to the online Astronomy and Space Science Seminar Series of TÜBİTAK Research Institute for Fundamental Sciences. We organize this seminar series for national and international audiences in this difficult period of life to mitigate the negative impacts of COVID-19 situation on scientific thoughts and science-based actions. It is my distinct pleasure to introduce our today's very special speaker, Professor Louis Lehner from famous Perimeter Institute for Theoretical Physics in Canada. He is going to give a great talk entitled Ubiquitous Black Holes and Gravity in the 21st Century. We will have a question-answer session at the end of the talk, where questions can be asked by using the chat button of the Zoom platform. Professor Lehner is a very well-known physicist who focuses on understanding strongly gravitating systems, both in 4- and high-dimensional space-times. His research spans a broad range of topics, such as systems containing black holes and neutron stars, systems able to produce strong gravitational and electromagnetic signals, tests of alternative theories of gravity, numerical relativity, and multi-messenger astronomy. Professor Lehner is recipient of a number of awards and fellowships. In particular, he is the recipient of Nicholas Metropolis Award of American Physical Society and Alfred Sloan Fellowship. He is a fellow of the American Physical Society and the fellow of the International Society of General Relativity and Gravitation. He is also a member of Scientific Council of the ICTP, South American Institute for Fundamental Research. With this, I want to thank once again Professor Louis Lehner for joining us for this seminar and look forward to his talk. Louis, you're welcome to begin your talk, please.
Well, thank you very much, Alikram. That was a very nice intro, undeserved, of course. And it's a pleasure for me to try and join you as a part of the world that I have yet to go to. But I have had tons of interactions with excellent scientists from Turkey, and I'm always impressed by what I get to hear from them. So my talk, is anchored in black holes, and you'll see why. And as we go forward, I'll try to present some of the interesting developments that are happening, and this is just a prelude of a lot more to come. So we're at a distinct corner point in the study of gravity in a very large sense, and I'll try to touch upon the general picture first, and then we're going to go into more and more detailed examples of what is going on, and which, as I said, is nothing but a trailer of the amazing things that will happen down the road. So ever since, I don't know, as a species, we gain conscious and try to understand our surroundings, we've been using messengers to try and understand our role in the universe, and how everything behaves. And in some sense, it's the platform for physics, which is a discipline that wants to, in some sense, understand everything that happens, and with that predict what will happen. So very early on, we were using electromagnetic waves to learn from our universe. As we moved on towards the tail end of the 20th century, we added to the electromagnetic waves particles, both in the form of neutrinos and high energy cosmic rays, produce even more information about our surroundings. And very, very recently, gravitational waves have come to this list of messengers we use to explore where we are and how our universe universe behaves. So modern day gravity understanding, as you know, had a major revolution with Einstein. About 100 years ago, he threw away the way we understood gravity a la Newton and postulated that we had to have a new and radical way of thinking about gravity, not as something that is mediated by forces, but the ability of mass and energy to curve space-time. And this curvature is what determines trajectories and the way the universe should behave at large scales, where all the other forces are much too weak to compete with gravity. And we understand that as higher densities, which will mean stronger curvature, and these will produce some strong effects, which at some point will be clearly discernible from those that we would have predicted or understood using a Newtonian way of thinking. So in his way of thinking, the gravitational field will be essentially kind of given or directly determined by in some sense, the amount of mass we have in some given scale. Let me turn on the pointer, which say if the scale is L and the amount of mass in that scale is M, so that ratio will give us the gravitational field, and the ratio of M to the square of that typical length scale give us the curvature. And curvature becomes a major ingredient in his theory. And it is at the largest curvature and the largest gravitational field where we're going to see, or we will predict significant differences with respect to Newtonian mechanics. In particular, this curvature can be so extreme that we'll create this object, theoretical object for the first 50 years or 60 years of the life of general relativity, which we call a black hole. And that's a region where the curvature is so intense that not even light can escape at the classical level. At the quantum level, there are ways around it, but it still is a very enigmatic regime of the theory that is still unresolved. So we're going to keep, for the most part, the discussion on the classical level. It's sufficiently interesting without going there. And eventually, the way we should modify our theory to try and include quantum effects will be hopefully sufficiently informed by observations that will tell us what the right direction should be. So as I said, black holes are kind of an extreme prediction of general relativity, but which took a while to take hold. But early on, people did take other features of the theory seriously, in particular, bending of light. The idea that the space-time becomes curved enough that null rays or light rays as they go around have no choice but to kind of bend its path as a response to the curved space-time. This was one of the tenets of one of the basic tests of general relativity after its inception, and has been used all throughout astrophysics and cosmology. This is the way we understand dark matter exists. And this is also the way currently some exoplanets are being discovered. So this is a very early prediction of general relativity that had a significant impact on current day research. And so both practical and fundamental questions can be raised through these observations. Of course, as any physical theory that is sufficiently interesting, physicists will try to test it and stress as much as possible. And so this is a slide that was created, or a picture that was created recently for a science report that compares all the ways, all the regions where gravity has been tested or general relativity has been tested. And in the vertical axis, what you see is curvature, some radius of curvature. So it's some combination of values that will tell you how curved the space-time is around some certain regions and where the experiments have reached. And in the horizontal scale, what we have is this potential field. So a black hole sits way, way to the rightmost end of the scale. A black hole is by definition, pretty much, when m over L is order 1. So any test that we do on Earth sits way on this side, because both the curvature of Earth and the gravitational field of Earth are small. But as we go to the right and up, we are stressing both curvature and fields. So a black hole, as I said, has m over L of order 1, but a supermassive black hole, a black hole that has millions or billions this mass of our sun, has a curvature that is much, much lower than a stellar mass black hole that has of order hundreds at most the mass of our sun. So as a result, two of the examples I will describe a little bit during my talk probe different regions. The Event Horizon Telescope looks at or has as a target supermassive black holes. Because they are black holes, they are sitting here on the right side of this axis or this plot, but they are not going too far up. And that's because the curvature of a supermassive black hole is much smaller than that of a stellar mass black hole. And it is left to gravitational wave observations to probe this regime. But both are stressing the theory on one end, the m over L side, and significantly on the curvature side, especially so the gravitational wave targets in the stellar mass black hole cases. And of course, the hope is that as we stress the limits of observations of the theory, cracks in general relativity might begin to show, and slowly these deviations might tell us what should be the way general relativity should supersede it, or if no deviations are seen, at least what significant constraints on putative theories that have been put forward can be provided. So just two examples here of the two that I was mentioning about, the EHT and Ligos on the top frame. This is an example of what type of combination of telescope is employed by the Event Horizon Telescope collaboration to effectively make the Earth a lens of the diameter of Earth. And as a result, it gives for the right sources, and these right sources are supermassive black holes that are not too far from us, so in galaxies that are close by, or our own supermassive black hole at the center of our galaxy. And this was a celebrated picture that was communicated to the public a few years ago. And just to give you an example, or a very telling figure of merit of how accurate this array of telescopes can be in accounting for scales, the effective scale that this network achieves is enough to, if you were to put a plate of locum on the surface of the moon, you should be able to count how many they are in such a plate. And this is how the image of this black hole in a galaxy nearby, M87, was produced. And what we see is the structure of a putative accretion disk that is shining very brightly, comparatively speaking, due to the strong effects of the strong gravitational field of black holes that make this matter swirl around at such a high velocity, increases the temperature, and induces it to radiate in a way that can be observed by this network of telescopes. On these others, on the bottom side, I'm showing a picture of LIGO. This is one of the two laser interferometer gravitational waves observatory that were built by the US. This is the one in Louisiana. It has 4 kilometers arms, and we'll discuss why in a second. It's trying to detect a very, very tiny signal in the noise, but it achieves it in a very clever way. And the figure of merit that we should keep in mind is that it's, in a sense, able to measure in the right frequencies the distance from the sun to our closest star, which is at 40 trillion kilometers away from Earth, with an error in the distance that is about or smaller than the size of a human hair. Technologically, these are ridiculously impressive feat. And as human beings, we should be very, very proud that we have gone this far and keep pushing the envelope of technology. So let me just take a little bit of a step back, tell you where black holes, some basics of black holes and how and we're going to move forward from it. So as described from the theory from general relativity, black holes in the universe should be described by only two parameters. Of course, there are some assumptions, some strong assumptions in this statement. One is that they are stationary. So a black hole is not changing at all. It's just steady there. And if we find such a black hole, the theory tells us they should be described only by two parameters, mass and angular momentum, regardless of what we use to create them. So we could compress regular matter, we could compress energy through, I don't know, electromagnetic energy or whatever, as long as we put enough mass in a small enough region, m over L of order 1, then the black hole at the end of the day will have the same end regardless of what we make it with. And this angular momentum is the rate of rotation of the black hole, and that should be it. Of course, the theory also tells us there is a one-way membrane. This membrane or this region of the space-time where you can only fall in and not come out at the classical level has a size of order 2m, so twice the mass of the black hole. In general relativity, the mass is a length scale. So for a stellar mass black hole, m is of order of a kilometer. For a supermassive black hole of 1 million solar masses, it's a mass of 1 million kilometers. And this membrane is at m for a black hole that has no rotation whatsoever, and is order 1 for order m, sorry, for a black hole that rotates at its maximum speed, at its maximum rotational rate. Another cute thing that the theory predicts is that there are no stable circular orbits inside some radius that is slightly larger than this, not too much larger, but within that radius, you have to fall in. Beyond that, you can keep rotating for a while, unless you're emitting gravitational waves, and we're going to get there. But once you're inside that radius, there is no way out. You're going to fall in if you there are no stable circular orbits. All circular orbits slightly perturbed will just fall into the black hole and it's gone. Another basic result, this result by Hawking, tells us that the maximum energy we can extract from a rotating black hole is 29% of its mass. If we are able to do that, that says that basically almost a third of the energy of an object can be extracted. And this is an outstanding figure. As a comparison, nuclear fusion is just 0.1%. It's a very, very small. So this is if we're able to do that, the extraction of energy through gravitational means would be the most efficient way of producing energy out of matter that we can know of. And the last thing we knew, again, this is now going to the 70s, is that the black holes are to be stable. Of course, mathematical proofs came later, and some of them are still coming out. But for a physicist, by and large, we regard them as being stable just because we can study linearized perturbation and realize that all those perturbations decay away. But more importantly, they decay away with a way that is very, very well defined. We can define many modes using, say, spherical harmonic decomposition, and each individual L and M combination decay with a very, very prescribed way in terms of M and A. And this basically puts forward one of the most stringent tests of general relativity around black holes, which says if you measure one of those modes correctly, you determine the mass and the A, which you can do with a single mode, you immediately know what all the other modes should behave like. And a measure of a second mode will tell us immediately if such a mode is behaving as in general relativity, or we're already beginning to see cracks in the theory. Armed with those very basic observations, black holes have been an anchor for black holes in astrophysics and beyond. We have been using as the engines of some of the most spectacular events in nature. So an example here in the left is a quasar, where we see very collimated outbursts or outflux of energy that goes for a scale that is much, much larger than the galaxy itself. How come this is happening? It's one of the major questions in astrophysics and the formation of jets. which again, at the center, it needs to, in the most robust models, it needs to have a black hole. But towards the end of the 20th century, black holes found their curious way into some much broader context, not just astrophysics, not just fundamental physics itself, but in a way it has gotten into every other piece of physics we can think of through this purported holography between anti-de Sitter, gravity and anti-de Sitter. Forget about the words. If you're thinking of general relativity with a negative cosmological constant, of course, a negative cosmological constant is not what we think the universe has, but at least from the formal level, we can entertain the negative cosmological constant. And through work from 't Hooft, but cemented and further elaborated by Juan Maldacena, this holographic duality has been put forward that basically links gravity in some given number of dimensions to conformal field theories in one lower dimensions. That is, if you're interested in studying superfluidity, superconductivity, for instance, in a particular conformal field theory, you might as well do the calculation in a completely different setup. You forget about where you came from, and you just do gravity in one higher dimension where you have a black hole interacting with some fields, and by understanding how they behave, you may be able to say something about what the field theory is doing. So this is a very, very interesting branch of physics that stemmed from string theory, but is now being pursued by condensed matter theories, quantum information theories, and is seeing its head raised in many, many fronts. I'm not gonna go into this, but I'm happy to answer some questions if there are. I have done a little bit of work on this front. I'm definitely not an expert, but it's a very interesting way that to see gravity and black holes playing a potential major role to untangle some very interesting questions, which in principle, one would not have thought had anything to do with gravity. So let me go back to now gravitational waves. So how do we understand gravitational waves? This came out of in a paper by Einstein, where he initially doubted their existence. In fact, the original version of the paper was about the non-existence of gravitational waves, got corrected by the input of a referee. And eventually the paper essentially changes its focus from the non-existence to the existence. But that's another virtue, I guess, for the refereeing process in peer review research. So there is where we say, well, suppose you, to answer the question sufficiently complicated, so let's simplify. Let's imagine we go sufficiently far from any highly curved region. We understand that Newtonian theory there is not too bad. Newtonian theory purports that the space-time is flat. So we know there will be some small perturbations. So let's include them in our assumption for what the metric that describes this curvature of the space-time is doing. We plug that into the equations of motion of general relativity. And what we find is that this metric perturbation obeys a wave equation with a source that this is where we link to the region of the highest curvature. But the important message here is that the theory itself provides a way for perturbations to propagate following an equation of motion that is exactly or very much like waves in flat space-time. So that immediately tells us that the gravitational waves are propagating at the speed of light. They are transversal, and there are only two polarization modes. And the generation is linked to what the source is doing, and in fact, it's linked to the acceleration of the source. So the quadrupole of the source, the acceleration, how rapidly it's changing, tells us how strong the gravitational waves would be. As a result, remember I showed the picture of LIGO, which were two L's. That's the reason, interesting. I guess I have to take the pointer out. Hold on. Bear with me a second, please. I had a movie here that was good. Oh, I can't play the movie. Okay, sorry about that. I'll try to do this different way. Okay, there it is. So what you see here is a circle, a ring of particles with a wave that is going through it. And as we said, the gravitational waves are transversal. And so what they do with a circle is they just introduce oscillations that deform that ring of particles, stretching in one direction and compressing in the direction that is orthogonal to it. And this process oscillates through time. And this is the reason why LIGO is built in that L shape, because it tries to maximize its effect to give the best possible way or the best possible chance of detecting a wave that is going, as in this second picture here, that is going traversal to it and will shrink one direction, expand the other one. And by very carefully measuring the time of arrival of laser photons that go and bounce off the end of the mirrors, and being able to essentially prove or argue that no other disturbance has happened, they can argue this gravitational wave has seen. Of course, the addition of more than one detector and a lot of hard work goes in here to, at the end of the day, say this, we believe a gravitational wave has been measured. And I'll say a few more things on that. Of course, one may ask, okay, what is the goal and why is it that we are so interested in going after gravitational waves? Well, the first, some answers or several points would be to answer the question, is generativity consistent with nature in systems where m over r or m over l is close to 1 and the velocities or natural velocities of propagation of the objects that are producing these gravitational waves are of order 1. If we detect them, not only we can answer the first question, we can also start looking at trying to infer the population and existence of the objects that produce them, in particular black holes and neutron stars. These are the objects in nature we believe have the strongest gravitational fields associated to them, and as a result will produce the strongest gravitational waves. So with that, we can begin to do a population analysis of these objects that is independent of that we would do with electromagnetic observations. And I'll discuss more about this as we go along with some of the examples of observations that have been produced. Because one of the objects, as I said, is neutron stars, we'll be able to study the behavior of cold matter at supranuclear densities. So neutron stars have densities that are larger than nuclear densities. And because one scenario of gravitational waves that we would observe is the collision of neutron stars, the collision would produce a very hot object. And then we can ask the question also there, is matter at supranuclear densities and hot behaving in what ways, and how we might learn from that for theory, a theory that is still not existent. And of course, the combination and the complementarity of observations of both electromagnetic and gravitational waves, and maybe also particles, will give us an amazing peek into the inner workings of some of the most energetic events in the universe. And of course, whenever you open a new window to the universe for exploration, there might be surprises. And we'll discuss a few of those. Just to give you a source estimation and why is that we keep talking about black holes and neutron stars, we can make a few back of the envelope calculations to tell what is the strain, what is the deviation, the relative deviation we expect in LIGO, and why. So if you go through the theory, essentially the strain that an object, a source that has mass m and is within some scale r, produced at an observer that is a distance r away, is essentially the gravitational potential at the source times the gravitational potential at the observer. So that gives you some estimate. And if you put neutron stars, which is what I have here at the bottom, that gives you a relative change in size that a gravitational wave will produce. This thing we call strain is of order of 10 to the minus 21. This is why the LIGO had to be capable of having the technology of measuring what I use as a figure of merit, the distance from the sun, from us to the closest star to our sun, with an error smaller than the width of a human hair. The luminosity, again, through the theory, is essentially the Planck luminosity times some power of the source compaction. So the closest we can make this to 1, the stronger the luminosity will be. And a black hole has this being 1, and a neutron star has this being about 0.1. So this would be the strongest conservative sources that we can think of in our universe, able to produce the highest luminosities. So LIGO's noise curve. So how does LIGO manages to achieve this amazing sensitivity? Well, they fight with a lot of things, and these are a lot of curves here. I'm just indicating the initial LIGO design specifications and something that the very early incarnations of LIGO would have, how it's going to this better curve that is more than an order of magnitude better in sensitivity. So here what we have is the strain, how small a value we can measure with respect to frequencies. And you can see that once LIGO reaches design sensitivity, it's fighting with very interesting sources of noise. So some of it is quantum noise. So LIGO is able to see the noise produced by individual photons hitting the mirror. And the future incarnations of the detector will actually be using quantum non-demolition techniques to further improve here. At the low frequency regime, they actually have to fight with seismic noise and Newtonian noise. The gradient noise, that small, non-homogeneities in the structure of the density that describe Earths produce tiny variations in the gravitational field, and that in itself moves the mirrors a little bit. So LIGO is pushing onto all these limits, and technology is going up to the bottom ends of what we could do on Earth with current technology, and further technology being developed for future generations. So this is as far as gravitational waves measured from Earth-based detectors, but there is more. There is a mission called LISA and a few others that are being planned in China that will have a similar detector, but in space. And the arms, instead of being separated of order kilometers for the gravitational wave observations on Earth, this is order millions of kilometers. And their target is primarily not stellar mass black holes, but supermassive black holes. And then there is this other one where we actually use pulsars, or people use pulsars, and time the arrival of signals from the pulsar. And if a gravitational wave were to go through in between Earth and the pulsar, will either stretch that distance or compress that distance. And as a result, the arrival timing of pulses will be modified slightly. And by a lot of statistical analysis, they can dig out the gravitational waves that would have gone through. And there are 3 collaborations using of order several dozen pulsars, and they are close to coming up in the next few years with their conclusions as to the presence or not of a background source of gravitational waves from the universe. So if you put all this together, well, there are the ground-based interferometers targeting the frequency range of, say, 10 to a kilohertz. These are for stellar mass objects. Then there are the space-based interferometers targeting supermassive black hole mergers or stellar mass compact binaries that are further separated apart. And these are ranging in between 10 to the -2, 10 to the -5 hertz. Pulsar timing arrays, the ones that use pulsar on the time of arrival, this is even lower frequencies, 10 to the -9, 10 to the -10. And this would be all direct measurements of the impact of gravitational waves in separations. And then there is a lot of efforts in exploring the impact of gravitational waves in the early universe, which in themselves would impact on the emission of photons, and one could try and extract them from the cosmic microwave background radiation. How does LIGO achieve this? My initial figure showed a lot of noise, but the signal was buried in it. Well, the way we bury, the way we dig signals buried from the noise are many. One of those, the one that is the most efficient one, is to have some a priori knowledge of the type of waveforms we would see, and then convolute the expected waveforms for a whole bunch of potential sources, and just do kind of an inner product weighted by the noise of the detector, and this is called match filtering. So this requires models. This requires theory to tell us what should be putting in this operational calculation. And this, of course, then turns into theories to try and produce this input and a lot of data analysis. Of course, there are other options like looking for bursts and model sources, etc., that are more agnostic with respect to the theory. The price to pay there is the sensitivity, or the signal to noise ratio is much lower when you use these techniques than when you use those ones. Every now and then you would have a signal that might be so strong that you can actually find and search with this one without having even gotten your act together with match filtering. Luckily, the first detection got both of them. And I'll describe that later. So now that I mentioned we need to, or you would want to perhaps ask theoreticians to give you guidance, then you ask them, how would the system behave? This would be the equivalent to the two-body problem in Newtonian theory, but in general relativity. It is much more complicated in general relativity because of many of the intricacies of the theory, and I'll give you some examples. But this is how a theorist would approach the problem. We'd say, well, early on, when the objects are very, very separated, we know Newtonian theory should not be too bad, and we can compute how bad the theory would be at trying to reproduce the system, the behavior, and it's actually pretty good. And you can tell that if the physics were governed by Newtonian theory, these objects would never come together because orbits are stable there. So there are other physical effects like dynamical friction and body encounters, etc., that bring the orbit closer and closer. As this happens, gravitational waves generation that take away energy and, more importantly, angular momentum from the system will tighten the orbit, will make it closer and closer and closer. The frequency will go higher and higher and higher. And the corrections of general relativity with respect to Newtonian theory will begin to play a significant role. So you can do a sort of Newtonian calculation, which we call post-Newtonian. So it's Newtonian plus corrections that come guided by the theory of general relativity. And you can begin to understand how the acceleration of the objects, in particular the radial acceleration, will behave with respect to the physical parameters of the system. So of course, at the leading order, you have the Newtonian calculation, but then you have different couplings, spin orbit couplings, etc. And at a term that goes like the mass of the system divided by the separation to the fifth power. So this is a tiny number first, but it gets larger and larger as the objects are coming together. This is where gravitational radiation kicks in. This is what drives the object in these spiral regimes to get closer and closer. And if you keep going further, you have to go to m/d to the 10th power, so a much tinier number, to begin to tell the structure of the objects. Where these objects are black holes or neutron stars shows up here. And you can imagine that regardless of how strong the tidal effects are, because they are multiplied by this tiny number, at very early times, this would behave like 2-point objects without really knowing what the structure, what their nature is. And only towards the end will this effect be sufficiently strong to produce sensible departures. And hopefully I'll get to show you some examples. Of course, at some point, these objects will just hit each other. And let's imagine for the time being that they are black holes. So as they hit each other, we really don't know what to do. We need to get numerics to fully resolve the system. But then afterwards, if it is true that that nature wants to produce a black hole that is one of these stationary black holes, we would think that the perturbations of that final black hole would be enough. And I'll tell you that this is enough. I'll show you an example. But the intermediate one, how do we go from the spiral to the late behavior we needed to use computers for? And that tells us we need to access the truly nonlinear regime of general relativity. And I would argue that's another part of the revolution in the 21st century. A lot of the physics 20th century and before was driven by linear analysis, pencil and paper calculations that often relied on some assumptions that were there because we couldn't calculate other regimes. But here is where I always bring back this example of this quote by Stanislaw Ulam. The term nonlinear science is like referring to the bulk of zoology as a study of non-elephant elements. So in my mind, physics is nonlinear. If we're in the linear regime, we're in a regime where we more or less know what to expect. And it is the advent of powerful enough computation that is opening a new window into physical systems that we didn't have access to before. In some cases, they give us very strong surprises. In others, just reaffirms our intuition that we built through linear analysis, but it's good to have the tool to even ask that question. So what happens when two black holes collide? So this is a movie that hopefully shows you how these objects, these are two black holes, are not of equal masses. As they are going together, these waves are departing from the system. They're carrying away angular momentum. The orbit tightens. The frequency gets higher and higher. Eventually, a merger happens. And voila, you get something that is fairly innocuous, very simple. So let me just show you here. So this is the same waveform that I showed you before. Forget about this early piece. It has to do with some of the definition of the initial data. If you forget about that, then you have this sinusoidal thing that gets higher in amplitude. This is something related to the waveform itself. Higher in amplitude and higher in frequency. The merger happens, and here I'm zooming in the bottom plot, I'm zooming into this region, and you see again the sinusoidal behavior, the amplitude goes up, and then it begins to go down again. So the numerics were able to tell us that in this very, very nonlinear regime, the system does not behave too crazily. It just, in essence, kept going with the trend that it had before in a much more violent manner. The black holes got together, form a single one, and very quickly, exponentially quickly, the black hole, the system wants to relax to that purity black hole described by a mass m and spin a, which we can understand once we study the full system, how much the late m is related to the individual mass 1 and mass 2 that the objects had, and the final spin a had to do with the individual spins that the system has, the size of the objects, and how they came together. You can also extract how much energy came out, and this is depending on the parameters of the system between 3 and 12% of the total mass. So an incredible amount of energy comes out in the system, and I'll describe some more as we go along, in a very, very short amount of time. Let me change a little bit. Suppose now that instead of having two black holes, we have a black hole and a neutron star, or two neutron stars, and what would happen? So if we have a black hole and a neutron star, well, remember I mentioned there is this thing called the innermost tailboard circular orbit. So depending on the mass of the black hole and the spin of this black hole, that radius where you would have no potential of stable circular orbits might be larger than the radius at which these gravitating objects will produce tides so strong in the neutron star that will disrupt the star. So if this radius is larger than the tidal radius, the one where you disrupt the star, this star will just be swallowed whole by the black hole, leaving essentially nothing that will tell this was a neutron star as opposed to a black hole. So if you're in that regime, the behavior will be exactly or very much like the one we just saw with two black holes coming together. If on the other hand, because of the parameters of the black hole, the innermost stable circular radius is smaller than the tidal radius, then you're going to disrupt the pool star, you're going to destroy it, matter will be thrown away, and you're going to form instead a black hole with an accretion disk. If you have two neutron stars, well, the same could happen. You could collide these two stars. If the stars are the final object is too massive, a black hole will form with some matter outside, and you're going to have a black hole interacting with an accretion disk. Or if the stars are sufficiently not very massive, then you might form a very distorted, differentially rotating object that is not a black hole, but a very messy system governed by the same equation of state that described these two stars to begin with. Of course, the impact, this is in the very short scale, very close to the objects. Much further, well, they could be doing lots of things. So for instance, this is a movie that we did almost 10 years ago of two black holes interacting with plasma. So as these black holes swirl around and significantly distort the space-time around them, just forces this plasma and transfers some energy of the rotational energy of the system into the plasma and powers this jet. So very much like these quasars, where we had a single jet, black holes, binary black holes are able to produce two jets while they are going around. Eventually they merge and give rise to a single jet produced by the system in much the same way that we think is going on with quasars. So that was a prelude, a lot of theory, but finally we did get it. And so this movie has sound. I'm going to play it. This is the gravitational wave that actually was heard in LIGO. LIGO, I told you, is measures between about 10 hertz and a few kilohertz. So some part of that is in the human audible frequency range. And in fact, the very first frequent black hole that was measured was within that. So the gravitational wave that you'll hear if you hear the noise, the first time the movie plays, it's in the original frequency. It's hard, it's there, it's kind of low. It might be hard to hear. Then it's going to play again with a frequency that has been increased by a given factor to make it more easily audible by us humans. So let me just play you. Whoop that you hear at the end is a slightly increased natural frequency of the system. This was extremely short time. So in the right-hand side, you see the plot of the duration of the signal as seen from the detectors. So it's less than 0.5 seconds. Within that amount of time, the system emitted about 3 solar masses. So the luminosity is ridiculously high. It completely outshined the rest of the universe combined. So if we combine the energy that is emitted by 10 to the 11 suns per galaxy in 10 to the 11 galaxies, this was much stronger than that. And of course, it's kind of ratty, but okay, this is the experiment. But the ratty behavior is very consistent with the gravitational wave produced by 2 solar mass black holes of masses of the order of 30 solar masses each. It's very consistent with general relativity. It was extremely loud. It was very close, very large black holes. And so it result both the match filtering technique and the burst search were able to capture these. This was the very first observation, and it was amazing in more than one way. Not only did it mark the beginning of gravitational wave astronomy, but it also provided the first surprises. And the two initial surprises were, wait a minute, these 2 black holes are ordered 30 solar masses each. Up to that point, most models of formations of black holes were not happy with such a high mass. There were some, if you push them, that could give you such high mass to begin with, but it made people, quote unquote, uncomfortable in the sense that it was an opportunity, good uncomfortable. It was a good opportunity to go back to the drawing board, and very quickly, some other mechanisms were put forward that would more comfortable give such masses. Not only that, the black holes here are consistent with essentially having come together, the individual black holes with no spin. So not only did you have to form them with significant mass, but you also had to form it with relatively low spins, or spins that were fairly misaligned with respect to the orbital angular momentum of the system. Those were already puzzles, interesting puzzles from the very onset. And this was just 5 years ago. Some time later, this just 4 months later, 3 months later, there was another signal. Now this signal was not as nice, was much weaker. The system was further out. The masses were lower. And it did require this match filtering to take place. But of course, now you can go with the confidence that you have detectors that were able to detect gravitational waves thanks to the first one. So the first one was very good in more than one sense. So here, just in virtual time, I'm not going to go through this list. This was the very first one. So if you see here is 15, 15, 117, 317s. These were the very first incarnations of LIGO, the very first physics observing runs in the new era of LIGO. One of the quick things that you could do with this is to say, because you're receiving gravitational waves at many different frequencies, if you have a theory that suggests that the gravity has a mass, it's not a massless object, but is massive. The fact that you're observing at different frequencies lets you put bound on the mass of that graviton. So with just the very first observation, gravitational waves were able to put a bound on the mass of the graviton of 10 to the minus 22 electron volts per c squared. And just to put in context, decades or centuries or however long you want to put of electromagnetic observations has the mass of the photon with a bound that is not as good as is 10 to the minus 22. So as I said, there were puzzles associated to this. These were the very first observations were the masses, okay, we seem to, or the masses were a bit too high. People had to go and kind of tweak a little bit the parameters of their formation model. Also introduce new formation model mechanisms. The spin was a puzzle. Of course, once you go through that, this is astrophysics. But then there is general relativity or fundamental question. Is this really a black hole? Does it behave as what you expect in general relativity? These signals, even though they were strong to be observed, they are still not too strong or not too many to really tell us if the black hole behaves as a curved black hole. Remember, I mentioned that if you measure more than one decay mode, you can put a significant constraint to general relativity. Well, we have not yet been able to do that. The signals have not been sufficiently strong, or the signal to noise has not been sufficiently strong. But there is a very tantalizing possibility to stack multiple signals and gain sensitivity that way. And this is ongoing. So soon we're going to hear more about this, I expect. But LIGO kept going. The detector kept improving. And this is the latest one. So now look at all the signals that have LIGO have communicated. Many, many, many. Not only we have many more events, but we have events that keep pushing the envelope. So some of these, for instance, these two objects, so the two black holes coming together produce a third black hole. But these two black holes, look at this one. This one has a mass estimated of about 80 solar mass. So it's an individual black hole that made it into a binary with another object that has close to 70. Both of that black holes, if you want to argue, are already kind of pushing strongly an envelope. There was a putative bound on the highest mass of the black hole expected due to some instability called pair instability, which in the understanding of formation of large stars put a bound on how high a mass could be before something else kind of take away support from the star through radiation. And you didn't expect black holes that were larger than 50 solar masses individually produced. So these ones with 80 are already saying, well, you need to go back to the drawing board. And if you tweak enough the parameters, you can make it, but it has already pushed the envelope significantly. There is this, but then there are ones that are sufficiently low. This one, 5, already pushes on another N, again, observations, primarily driven by observations on the electromagnetic side, which inform or bias, if you will, some of the theory that was produced, began to say some decades ago that you shouldn't be having black holes of masses lower than 5. Well, now LIGO has produced or has detected some black holes that are pushing the envelope on that and putting some interesting questions as to what the validity of those assumptions were. And it might have been affected by the bias of electromagnetic observations. I'm going to just give you a few examples beyond black holes, just to say a few more things and then try to begin to wrap it up. So remember, once we move or we think that the system may have at least one neutron star, some of the questions we would like to answer is what the equation of state is of the neutron stars, how we can connect with energetic electromagnetic events, again, populations, tests of generativity, and some cute question that always came about was the origin of heavy elements, and I'll mention a few things on that. So I already told you that tidal effects, the ones that will basically tell us, oh, a point particle difference by a black hole by this much and by a neutron star by this much, come deep in a post-Newtonian expansion where this thing is very small. So it takes the orbits to be very, very tight before tidal effects, what has the information about the equation of state, play a role. So this is a simple movie so that you see kind of the late stages of a neutron star merger. So this is showing the density at the equatorial plane of these two stars. They come together. This is a case where the stars were not very massive. So the object that is formed is a neutron star that is differentially rotating. One of the things that the movie also shows is matter being thrown out at a very large fraction of the speed of light, between 0.2 and 0.3 c, which will play a role in what I'll say soon. But if you're only seeing these on gravitational waves, this is what you see. This is the gravitational waves for 3 systems very much like the one the movie has just shown, where we change slightly the equation of state. So the only thing that changes is the radius of the neutron star. The masses are the same, the theory is generativity, and only till very close to the merger, gravitational waves begin to differ. Prior to that, they were exactly the same. So here is zooming in some of the difference you see as you vary the equation of state, which here have labels NL3, DD2, SFHO, which are names at which there is no need, not necessary to go in. But whether this SFHO, so the bottom one differs from the top one by the radius of the star. In the top one, the radius is large. In the bottom one, the radius is small. So the star is more compact. So the more compact we make, the harder it is to tell the tidal effects apart, because this factor here that is multiplying that tiny factor gets smaller if the radius of the star is smaller. So this is to say, gravitational wave observations of binary stars in principle tell us about the equation of state, but we require significant signal to noise. And by virtue of the size of this object, the merger happens on the kilohertz range where the current detectors are losing sensitivity. So it will take a while before firm conclusions can be made. But LIGO has already, with what it's seen, thrown away some of the potential equation of state for large radii. I mentioned this thing about heavy elements. So one of these things that very cutely happens is this system, as you merge to a neutron star, is that you have the ability to throw out a significant amount of matter that is very neutron rich. Because of that, our processes can begin to combine these neutrons and produce heavier elements. And you can go all the way to the lanthanides. So the origin of heavy elements for the longest time was pointed towards supernova. But simulations kept pointing out that the ejecta in supernovas was not sufficiently rich to go all the way to the lanthanides comfortably. And once simulations of neutron stars, of binary neutron stars especially, and some black hole neutron star collisions started coming out, they started showing that this was a much richer, much more comfortable system to produce them. And LIGO finally, and so I'm going to now show you the example of LIGO, and you'll hear the waveform that was obtained for a collision of 2 objects, one of them a neutron star, because we did get electromagnetic signals associated to it. So you're going to hear the waveform from LIGO, and then a ping associated to the gamma ray burst observation from Fermi. So this is happening, hope you did get to hear that. This is happening routinely. So now gravitational waves, observations, and electromagnetic observers have lots of agreements whereby whenever LIGO sees something, and the earliest it can, it sends out a telegram or a message that is picked up by any observer that cares, and they point their telescope with whatever electromagnetic band they can reach and try to pinpoint the region that the gravitational waves is telling you the system is at. LIGO's sky localization is not great now, but gives sufficient small window. The very rapid turnaround scanning of electromagnetic telescope allows people to really pinpoint where the signal is coming from. So this happened in a very exciting way in August of 2017. It gave rise to these joint observations, both of gravitational waves and electromagnetic waves. And this here is an example kind of in the optical of having seen gravitational waves and gamma ray bursts. People were able to look into in this nearby galaxy, pointing the telescope, and you can see here very close, very soon after the merger, a very strong signal in the left, and then once you waited 14 days, it's gone. So depending on the band you're looking at, you saw very high frequency signals over low frequency signals, and in fact, this system people are still observing today, still getting signals from that event that collided at least one neutron star with something else. Let me not play this movie. This movie is not great, but this is just an example of as soon as this information was carried out, every single telescope that had time and could see that chunk of the sky pointed and saw that. And in particular, one of the things that was seen in the optical was something called a kilonova. And this is the remnant or the relics of this heavy nuclei process that I described before has. As you produce these heavier and heavier elements, some of them are very hot, they decay, they radiate away, and this produces a very clear signal that was captured by many optical telescopes. Just a cute example on the fundamental front, gravitational waves and electromagnetic waves, by having measured both of them, you can do things like, well, try and determine the difference in the propagation speed of gravitational waves and electromagnetic waves. Of course, theoretically, we expect both of them to be the speed of light, if we believe in Faraday's laws and general relativity. But if you want to entertain the possibility that maybe one of the two differs, you can use this event to put bounds, and they have put these are the bounds that have been put. Also, in the context of general relativity, conservatively speaking, electromagnetism is so-called minimally coupled to general relativity, and you can test that theory or that idea as well. And this has been done and put significant constraints. And you can also ask, well, what if some ideas coming from string theory or motivated by string theory are true, that maybe gravity feels more than 3+1 dimensions, but electromagnetism only sees 3+1 dimensions. This has also been kind of probed to some degree. And the number of dimensions of our space-time has been also bounded very, very close to 1. Sorry, not 1, to 4, 3+1. So when you ask, okay, what could this have been? Well, the most conservative or the simplest explanation is two neutron stars come together. They come together, they merge against each other with the speed close to the speed of light. So it's very consistent with the simulations. But then this matter gets thrown away. A significant amount of energy gets produced. A black hole is formed. This black hole interacts with the accretion disk that is around it. It generates a gamma ray burst. And what we have seen, what Fermi and other high energy observatories have seen, is that GRB slightly from an angle. And as a result, that explains why it was slightly less intense than typical short gamma ray burst. But it was the very first time where significant amount of observations pointed to the unique connection between short gamma ray bursts, a very enigmatic system, a very enigmatic phenomena, where a very clear understanding of what the central engine would be was not there, or was only there as a possibility from theory. At this time, actual observations connected binary stars with short gamma ray bursts. The cute thing of this system is that, okay, gravitational waves can tell you what the individual masses were. Those masses were in the comfortable range of observations of electromagnetic observations of neutron stars. But the byproduct of the merger produced, no matter what, one of the first. If it produced a black hole, it would be the first black hole recognized to be in the so-called mass gap, that regime between 3 and 5 solar masses that people to this point did not believe could harbor black holes. That if it produced a black hole. On the other hand, if it produced a neutron star, the neutron star would have had a mass of 2.7 solar masses. And if so, it would be the largest, heaviest neutron star ever measured. Of course, neither gravitational waves cannot access this yet. This is for the next generation of gravitational wave observatory, or for an event that happens much closer that will allow the degrading sensitivity of LIGO at high frequencies to still pick it up. And of course, as I said, there has been a unique, a very clear indication that binary neutron star mergers are a very significant element production mechanism, high element production mechanism. As we move forward, there are still puzzles. The equation of states has significantly been constrained, but not determined. So this will be, there will be more work here. The final state, as I just mentioned, is still unclear, not clear. Black hole neutron stars are still, maybe they have been observed. They're still not clear. We still don't have a clear smoking gun signal that black hole neutron stars have been observed, but this is coming. And more work will be invested in testing generativity as the theory is governing this system. So far, everything that has been obtained is consistent with generativity, but stronger constraints could be put, and people are working on that. So just to wrap up, let me give you my final thoughts. It's taken a lot of effort through 4 decades, arguably from as far as technology is concerned, to get to this point with respect to gravitational waves, and a lot more on respect with electromagnetic waves. I didn't say much about the Event Horizon Telescope, but you know, it's already targeting supermassive black holes, both at the center of our galaxy and a nearby one. It's giving very interesting insights as to the behavior of gravity, again, pointing to the consistency of generativity, but at the very least, it's giving us a peek into the very near structure of black holes on the electromagnetic side, just as gravitational waves are doing so, thanks to LIGO, Virgo, and Kagra. Future detectors are in the planning stages. These will be much more sensitive. They will reach redshift of about 20. So with respect to our understanding of how the universe progresses, this 3rd generation detectors will be able to see any binary black hole merger ever to happen in the universe. So this is just ridiculously high. The ability to reach at all confines of the universe is amazing. And this should be happening in the 2030s if these detectors are funded. LISA should be flying sometime towards the end of the 2020s, and will be targeting supermassive black holes. LISA sensitivity is much higher as well, and will give us unprecedented ways to test generativity, but also to do astrophysics. So gravitational wave astronomy is now on. It started just 5 years ago, and now has several dozens of events, and pushing the limit on both astronomy, gravity, and connections, and spurring connections between gravitational wave astrophysics and gravitational wave analysis and astrophysics through electromagnetism. But as I tried to argue, black holes are everywhere, not only here with us with astrophysics. We know black holes, so we have very strong indications that supermassive black holes have somehow some role to play in the very formation and structure of galaxies through this relation between mass of the galaxy to mass of the black hole. And even though a black hole is a tiny object in the scale of a galaxy, somehow they seem to interplay and regulate at least each other with respect to the size the galaxies will have and the connection with the size of the black hole. Black holes have found their way into many other branches of physics through holography, and the understanding, if not at least formally, of how black holes behave in general is playing a significant role there. But regardless of everything we've seen and will do, black holes are still enigmatic, still are posing deep questioning. We still have this information paradox problem. We still have this conundrum as how we're going to marry general relativity and quantum gravity. And the key to this will likely be our much better understanding of black holes. And with that, I'll stop. Thank you.
Luis, thank you very much for this very nice, deep, and exciting talk. I have also to emphasize with pleasure that Luis is a good friend of TBAE. He promises to visit us and stay for some time with us as soon as this coronavirus situation ends in the world. So then we will have many cases of discussions, and it will be very nice to see you here in person. So thank you once again for this seminar.
Thank you. A pleasure.
Now we can take some questions, I think, yeah? Questions, please.
There is a question in the chat by...
Yeah, through chat.
Yeah, by Dogan. So how is it calculated? So there are many ways of calculating this, Dogan. So the one option is to think, suppose you have a black hole that is maximally spinning, it's rotating. And I now imagine a process by which you take the rotation energy away. So you can say, well, suppose I take all the angular momentum. I don't take any mass as far as I can, but I have to respect that entropy, which is related to the area of the black hole, never decreases. So once you do that, so you're trying to maximize how much you can put in without violating the second law of black hole thermodynamics. That's how you get to the 29%. So there is a very clear formula. So remember at the very beginning of my talk, let me just say this. Now I went too far. So at the very beginning of my talk, I told you that the black hole of maximal spinning, this one, has radius m, where a over m is 1. So you say, well, suppose I have a black hole that has such a size, and I want to make it a black hole where the radius will be now 2m. So it's just a matter of asking, what is a mass to measure at infinity for one black hole versus the R-watt black hole? The difference of that is 29%. And there are different mechanisms. So you might have heard of Penrose process or the Branford-Snaig process. There are different ways where you can imagine taking energy away from a very rapidly spinning black hole and putting it somewhere. Of course, that is a very idealized, if you want, regime. In the much more natural scenarios where you collide black holes, this is where you see this up to 12%. So if you take two black holes, so let me just mention this thing. This size, suppose you have a black hole that is maximally spinning, it's close to A over M, close to 1. So because this black hole is very rapidly spinning, its effective size is small. This ISCO, remember this is the ISCO where this is the radius at which they have no choice if they cross that radius to just come together and merge. So if you are in the maximum spinning regime, everything gets tighter. So this radius at which they have to fall in is much smaller. So they can keep going around and around and around. So every time they go around, there is some amount of energy that gets produced. So if you think of this A over M very close to 1, they can go around each other many, many more times. So they can produce much more energy. So once you do that calculation, this is why you get closer to the 13%. So this would be in a much more natural regime where you don't ask for the idealistic kind of theoretical estimate of oh, I have this budget, I'm going to take it all out without violating the second law of black hole thermodynamics. Here you're saying, well, I'm setting up this dynamical system. I'm going to let these objects go around each other. I know that the closer they get, they go faster, they radiate more. But at some point, if they get too close, they come and merge into a single one and they stop radiating. And so that gives you this 12%. So there is another, could you talk, let's see. Could you talk about with black holes, gravitational waves, standard Sarans, and their own cosmology? Okay, oh, thank you, Fatih. Well, so we know, so us cosmologists have been using standard sirens for a very long time. This says that supernova behave in the same way, regardless of how far we're seeing them. And the only difference that will make a supernova that I see go redder as I go further out is this thing called redshift. So just as an ambulance going past seem to change the frequency of the signal, the same thing happens in cosmology as this universe is expanding and we keep seeing further and further back in time. So there is this very exciting idea of using gravitational waves to do precisely the same thing. So the idea is two black holes of the same mass colliding as predicted in general relativity will give up the same amount of energy. However, if I put this black hole further and further out, further and further distance from us, redshift will also play a role. So by using general relativity, by using the assumption that all black holes with the same mass are this, I'm simplifying the answer. All black holes with the same mass will collide in the same way. I give up the same amount of energy. If I see the same system further and further out, now by understanding how less energy I'm getting, I have a handle into the redshift, the behavior with redshift of the system. And that lets me do cosmology because now I have information on how the universe is behaving at different at larger and larger distances, which actually is earlier times in our universe. I hope that answers that question, Fethi. And one can do even better if you do have both gravitational waves and electromagnetic emissions, because now you can have a sense of distance, luminosity distance by measuring photons, and gravitational wave distance by measuring gravitational waves. And one can do an expansion graph over the history of our universe that is independent of the standard ones that use supernova arguments and standard cosmology. Hassan is asking, how would the measurement change if LIGO-Virgo experiments were conducting on the lunar surface and space? So if I were to put the same LIGO-Virgo configuration, so the only differences in LIGO and Virgo would be the sources of noise. So some noises will be, so the quantum noise would be exactly the same. So let me see where, I can't remember where it was. So here, the quantum noise would be the same. You produce a system that is completely insulated from the outside. You send the laser through the beam, and the photon noise will be exactly the same here and in the Earth. But the LIGO tubes are in an extremely good vacuum. And so it would have no impact whatsoever here. However, this Rn will change. The quantum gradient, the gravity gradient noise will be different just because the moon's gravity is different, and a tectonic plate movement on the moon, I think, are either non-existent or much lower. So the lower end of this noise curve will change. Where it will be better or not, that I don't know, but it would be different. So that's what I expect what the difference would be. So first of So Erdem, can future generations of the Liberator disturb spacetimes to create gravitational waves, or we always need extreme mass? Oh, this is an excellent question, Erdem. We can go back to this slide. So this slide basically tells you, so I like where you're going. So you want to create H to do it, to change the spacetime and produce a disturbance. So it has, you have to fight over two things. So here is how far you are from the source. So you say, well, I can get as close as I want because I'm going to be getting very next to the detector. Great, to the generator. That's great. You could do that. The problem is here. This is an extremely, this would be a very tiny number, just because the masses we have at our disposal, let's say, will be very, very weak. So this number for Earth is 4 to 10 to the minus 9. So they will be extreme, and so the GM over R, and then you throw in the C square. So it will be very tough. No, I don't think we can do it. The reason we are looking at very extreme, a very high dense matter is to get the best possible case here and observe to the farthest possible distance. For the type of things we have reasonable access to, we couldn't do that. So there's, hold on. What about the effect of charges of the binary if they're curved black hole? What charges? So there are two types. So I'm not sure whether where you're coming from with respect to what you call charges, because in some camps, the spin of a black hole will also be called a charge. But if you're asking charge as in electromagnetic charge, then they would be the same thing. So it would be the following. So imagine you have this object that has a charge somewhere in the universe. So if it has a net charge, either positive or negative, it will begin to pull charges of the opposite sign and neutralize itself in a very short time. So the understanding is that, okay, yeah, that's an electromagnetic charge. The understanding is that by and large, black holes, especially in the timescales we're thinking about, will be neutral. So you're perfectly right in that the Kerr solution, or the more general Kerr solution, has three parameters: the mass, the spin, and the charge. But in the context of universal, of black holes that would be regarded as the standard astrophysics black hole, charge is assumed to be negligible, because otherwise, a black hole with a given net charge, either positive or negative, will necessitate a universe where in its surrounding has that very same charge. Otherwise, it will discharge itself or neutralize itself. And then we will have to deal with larger problems. So we do have a universe where in some chunk, we only have a sign of charges of the same given sign. I think those are all the questions in the chat.
There's another one from Tahsin.
Oh, beautiful question, Tashin. In fact, your question is very actively searched for, and people are trying to put bounds on this. So the question is, it's a beautiful question. I think it's arguably the most important question, or one of the most important questions we have to grapple moving forward. Because in some sense, we're going to do better astrophysics. We're going to get more and more signals. We're going to get better and better understanding of sources. But as far as completely new understanding, it will come from to answer the questions as the one you're posing. Whether we're going to be seeing quantum gravity effect, that will be tough. But maybe they will manifest themselves as slight modifications of gravity. So some things that will slightly not work quite as expected in general relativity. And then as you begin to look at the deviations then there will be an interpretation. Suppose you get a deviation, and I'll give you some examples in a bit. That deviation may be because general relativity is incorrect, it's superseded by something else, and that something else might still be perfectly classical. That would be fine. So in that sense, we just missed the true theory, but or that true theory at that scale, but that deviation need not have yet anything to do with quantum gravity. It might just be that the theory is slightly different. or that deviation in itself stems from an effective effect from some quantum gravity thing. So let me give you one specific example. This is a colleague of mine works on this. So a black hole is supposed to be just a one-way membrane. At the classical level, things go in and nothing comes out. We know we have quantum arguments. It doesn't have to be quantum gravity because we still don't have a quantum gravity theory. So there are semi-classical arguments that say black holes will be able to radiate. Of course, this radiation happens at an extremely high frequency and low energy. So we don't expect to be anywhere near that. But let's entertain the idea that that regime is much closer. So it might be that as these black holes are coming together, you're generating these gravitational waves, you're going out. Of course, some of it goes into the black hole. In the way we understand in general relativity, classical general relativity, that thing that goes in and it gets lost forever. But now suppose, because of this further structure that the black hole has, some of this energy does not fall into the black hole, it gets to bounce and come out again. So that would mean that in your detector, you will see the main waveform coming out, and a slight time after, you'll see some little burst coming out. And of course, as this little burst comes out, we understand that there will be some back reaction. So that burst that comes out generates a little burst that goes in. But if using the same argument of what we used before, anything that goes in, we're going to allow a little bit that comes out, and this process repeats. So this is what people have been calling black hole echoes. And so people are actually looking for it. So far, I think the evidence is against this happening. Some people claim are much more optimistic, but I think by now the argument is strong that nothing is coming out. But let's suppose it is. If that's true, yes, it would be saying something very strong. Either that black holes are not, on the classical level, are not what we expect. There is some structure in there which has not been captured by general relativity, because general relativity will say there is no extra structure on the black hole, or that there is some fuzziness around the black hole stemming from some relic or some racing of quantum gravity head that is there. So it will be a fantastic evidence if that were to be seen. And then there will be lots of work done to try and interpret this one way or another, either as a classical deviation of general relativity, and eventually we all believe that sooner or later quantum gravity will have to raise its head. But where it's raising head in what you would see now, or what you're seeing now, is just it's just a slight correction of general relativity that has nothing to do with quantum gravity yet, or that is related to quantum gravity. This will be a fight that will be awesome to see developing, because it would have meant prior to that some evidence of some crack in the theory has already been seen. In terms of deviation of general relativity, what shall we expect from primordial gravitational waves? So primordial gravitational waves would not be seen by LIGO or LISA unless you change things significantly and there is some background that goes all the way to very low frequency, to very high frequency, sorry. I think some people entertain that. I don't think I'm qualified to answer that question. I think the most conservative or the most natural primordial gravitational waves will impact these modes in the CMB. There was a claim some years ago of some potential observations that pointed to that, but it was taken back. There was some slight over-interpretation of data in that front. I'm still waiting for the standard paradigm that will inform us of some of the flavors of inflation, if they are there, in the positive case. In the negative case, we still have too much freedom. But yeah, I don't think I can say more about that. Sorry, Tashi. Thank you.
More questions, please. So it seems that there are no questions. So Luis, thank you very, very much for this nice talk.
Oh, you're welcome. It was a pleasure.
If you agree, we can stop here. Yeah.
Sure, it's fine. Thanks everyone for coming.
So, thank you. Bye.
All right, bye bye. Have a good great holidays if you.
Yeah. You too.
Bye bye.
You too.